Okay, well, let me get started here. So project number 2 is due on Friday at noon. I will post the answer key shortly after Friday at noon. So it's important that you do get your projects in by noon on Friday. Okay? Also, I just wanted to remind you that you can work in groups. Surprisingly, no one worked in groups last time. I don't think I've ever had that before in a class, because usually, oh, group work, great. And all students love that. You guys, I guess, don't.
Well, I think we were all wanting to know for sure that we understood it. We were all kind of working on it, and then we were coming back and putting our heads together later to see if we come up with the same thing. So.
But, you know, you can do that too if you're working.
I know.
Just that's to help facilitate that process. Anyway, so group working is encouraged. Test number 1 is 1 week from today. And I have briefly talked about the format before. I just want to make sure it's clear. I completed writing the test last week. I will actually pass out a paper copy of the exam. And you can use R on these computers to do the necessary computations. So in other words, the computers here are like a fancy calculator. You will need to write all of your answers on the paper copy itself. If you have me for a class before, it's the same format. That's what we've had in the past. There's a formula sheet that I also completed. It's on the test web page. Just the various formulas from Chapter 2, just so that you don't have to memorize some long formulas. I will pass that out with the exam. Also with the exam, I will pass out the first 2 pages of this notation summary, which was given on the 3rd day of class. Just again, so I know the notation can be messy. You have access to that. The test is closed book, closed note, though. The only thing that you will have access to in terms of like notes is all my programs on the R web page. Okay. No, I will actually remove all the lecture notes from the website before the exam. I will also remove access to the videos as well. And just remember, I can see exactly what's on your computer screen right here. Are there any questions?
A quick question about the project. On number 2, part C, where it asks what are the empirical influence values, do you want to actually see the calculation of all of those at that point? Or do you want
with respect to the data?
Right.
So part A, you're actually giving me, let's say, the formula. So Y sub J should be in the formula.
In A?
I'm sorry.
So
why don't we start over? Why don't you ask your question again?
So in C, where you say what are the empirical influence values, do you want the formula there, or do you want also at that point the computations as
You're talking about
the data?
A, or you said C?
Number 2, part C.
Number 2. Oh, I'm sorry, number 2. I was looking at number 1. I missed the number 2 part.
Sorry.
Okay, so your question is. I was so focused on number 1 for some reason.
Where it asks what are the empirical influence values,
okay.
Do you want just the formula at that point, or do you want the computation using the data set at that point? Because I'd left the computation till part E, where I then compared it right there with the empirical.
Do the data set.
Only in E? Okay, so just give with the J's and everything in the formula.
In C.
Okay.
Oh, I'm sorry.
I just didn't hear you at first, but I got it.
Okay.
So no computations until you get to E.
That's right.
Okay.
Are there any other questions? Okay. We will take a little bit of time to talk about the project shortly. Let's first review. That's Stat 870. For some reason I never closed out that file. There we go. So we were talking about ways to estimate the variance of t. And we looked at the nonparametric delta method. And with that, we get VL is equal to 1 over sample size squared, sum j equal 1 to n of Lj squared. So Lj are the empirical influence values. Last time, we looked at a way that we could estimate Lj with the jackknife. And we call that Ljack J. And so then this leads them to an estimator Vjack, which is basically the same as VL. Except for now, we use these estimated empirical influence values. Sorry, we're hearing this lesson. First thing that we're going to do today is we're going to look at another way to estimate Lj, now with what we're going to call Lj hat. And this comes about through regression analysis. And this is going to lead to a variance estimator Vreg. And just remember, just also to remind you, remember we also have, we could say, I don't know if I used this notation before, VBoot, where if I were to actually take resamples, I would use this to estimate the variance. Okay. So that leads us then to page 46.
That VBoot is what we've also called like the bars.
Yeah,
Okay.
yeah. Sorry. Later today, that would be convenient to call it VBoot.
Right.
Okay. So we're going to estimate these empirical influence values via regression. It's kind of an interesting idea to do this. So to derive the empirical influence values, we needed to use this, what I basically characterized as a Taylor series-like expansion of our statistical function, T of F hat. Now remember that this F is the population distribution for Y. It's typically unknown. And T of F itself is theta. T of F hat is T. And notice also how the F comes into the empirical influence function. And you know, if you start number 2 of the project, and also like I just looked at number 1, I mean, you know that this means that this is going to be dependent upon, this empirical influence function is going to be dependent upon some other parameters. Now, what we can do then, since F is unknown, is, well, how about we replace it with F hat? And look what happens. A hat here, you have a hat here, and you have to make the corresponding change then to the stuff that's on the left-hand side too. So we have F hat star. And we've seen F hat star once before, and that represents, if we're thinking totally non-parametric here, the EDF for a resample. The EDF for a resample. F hat is the EDF for your original sample. And notice also how you get a star on top of the Y in the empirical influence function. Now let's think about what T of F hat is. Again, it's just T. T of F hat star then is T star. So it's this statistical function calculated on your resample, T star. So I can make that replacement. Then I'm going to do one other little change. When I calculate the influence function based upon f hat, remember, you basically get your empirical influence values. Okay? So that's why you see Lj there. And we know that for the yj stars, well, they can only be y1, y2, up to yn from our original sample itself. So what we could do, and we've seen this once before, we can change this to looking at basically the frequency. That's what f is. That's why the letter f is used. Look at the frequency the jth observation is in a resample. The first equation on page 47, the second equation on page 47 are equivalent. They're exactly the same. Just two different ways to look at it. That's all. Okay. So, let's think about what we got here then. The LJs, I want to estimate them. So let's think of them as unknown quantities. T star I can get from a resample. T we know. It's a constant. This F star we can get from the corresponding resample as well. So how about we view this kind of as a regression model? A typical regression model is, let's see, y is equal to beta 0 beta 1 times x1. Oh, if I write it like this instead, so I don't have to worry about that stuff. Okay. Well, what we're going to do is treat the LJs as the unknown quantities in a regression model, like your beta 1s. The F stars, we can come up with those. Those are like our predictor variables, like our x1. And then this T star is kind of like y. We can observe y, or we can observe T star if we take the samples. Since this T is a constant, what we could do is just simply move that over to the left side, and so that you're left with T star minus T is approximately the other side. And to further emphasize how we can kind of treat this as a regression model, in a regression model, let's say if I put an I here, I'll put an I here, you have a sample I equal 1 to n. Well, we could take a sample of R equal 1 to capital R, you could say. So here's an R. Let's see, put an R, just write it over here. We can put an R on the frequency as well. So our sample is essentially our resamples that we get, where each of the predictor variables correspond to F star 1, F star 2, down F star n. Our parameters, our slope parameters, are going to be our LJs. So, fit a regression model and estimate LJs. The way that our book does it, they make two small modifications. Instead of putting T star minus T on the left side, they put T star minus T star bar on the left side. Obviously, this T star bar is going to be something very, very close to T, and we just choose to do that instead. Also, pay special note, though, that there is no interceptor like you would have in a regular regression model. And also, we changed the sum that was on the right-hand side. Instead of going up to n, we go up to n minus 1. And the reason being is because these F stars, if we know F star 1 through F star n minus 1, we know what F star n is because we know what our sample size is. So that's why it's That's why we don't go up to the last one. Also, one can show that the sum of these LJs is equal to 0 as well. And this proceeds from, I kind of mentioned this last equation, 3.3, 2.33 in the book. It comes from there. So we only need to actually have in our regression model n minus 1 of the F stars and L and L's. So we do our regression model. Our estimated L's are simply denoted in our book by L hat. Instead of, let's say, L hat reg, we call it L hat. And then V reg is then, as you would expect, where we had an L before, we have an L hat. Okay. Any questions? Before we get to an example, 2 quick comments. So the various procedures using the regression model and the Jackknife tend to overestimate the true variance. And the nonparametric delta method variance, VL, typically underestimates. Now these are, notice the words typically and tend. Doesn't mean it happens every time. It just means that, generally speaking, this is what usually happens. And you'll see this in examples. That usually the nonparametric delta method will always be a little bit less, at least a little bit less than the Jackknife regression. Okay, so let's take a look at an example then. That's on page 49. AC data again. Remember, we're interested in estimating the mean lifetime for these air conditioners. And so let me go over here to 10. Get my data. And just as kind of a reminder here, when we work with the sample mean, the usual unbiased estimator would be, let's say, the sample variance divided by n. And the usual unbiased estimator then uses the usual correction, where instead of using the sample variance itself, you can take the sample variance times n minus 1 divided by n to get the usual bias estimate of the variance, and then you still have another n you have to divide by, since we're working with the mean. So these are what we're shooting for, you could say. So to do the Jackknife, I'm going to create an object called L.Jack gets. I'm going to use the EMP-INF function again, like what we did with the nonparametric delta method. Data equal y. Now for my statistic. If you remember from previously, we could use this calc.tw for the nonparametric delta method. The W basically stands for weights. You could do that with the Jackknife, but it's easier to use the usual form of a calc.t function that we've seen in the past. So here's my calc.t function. So calc.t function, passing my data, passing my indices. D gets data I, mean of D. S type stands for statistic type. I'm using indices in my statistics. That's why you see an I there. Nonparametric delta method, remember we use W for weights. Type equal Jack for Jackknife. Let's run it. And those are my empirical influence values. Let's use the regression. Let's get the regression-based estimates. Now, what you need to do first is actually run the boot function so you get your resamples. So I run the boot function like I normally do with my statistic calc.t that uses the indices. Put the results in boot.res. Do that. And then simply, for L.reg, gets EMP-INF, and now you say simply boot.out equal boot.res. That's all you need to do. So let's take a look at the empirical influence values, the estimates side by side, and notice they are exactly the same. That happens with very simple statistics like this. And in fact, they're exactly the same as LJ itself. So if I want to find now the variance, I could simply say var.linear l.jack or var.linear l.reg, or I can simply actually use the corresponding formulas, sum the L's, square them, divide by n squared, and I get 1417.715, and that's exactly the same as the bias estimate for this particular case. That will always happen. Any questions? So you can see working with the Jackknife, working with the regression-based estimators are a lot easier than trying to do the regular old nonparametric delta. And you often get results that are quite similar. Okay. So why is it important to find these variances? Just doing it for fun? Well, and I mentioned this at the beginning of this section, and that is, we're often interested in the following studentized value, t minus theta over the square root of v. Now, for this v here, we can use now 4 different possibilities. And all of them are estimated nonparametrically. Also, we will often want to calculate z star for the R3 sample. Now, to do that, you're going to need to calculate, obviously, t star for every single resample. Again, I don't know why I wrote it tilted, so tilt your head. But we also need that v star as well for every single resample. And if you're taking a lot of resamples, it's going to get a lot of variances. But we need that for the studentized values. So you can imagine, and this is something we're going to talk about next, but what do we do if we want to use the Bootstrap then to get this value? We're going to take a lot more resamples. That's coming up next. But before we get to that, first of all, are there any questions? Talk about the project a little bit more. So we already talked about number 2. We started talking about number 1 last time. Simply our statistic of interest T is the sample variance, theta is our population variance, A, just use the nonparametric delta method, get the empirical influence values, B, use the EMP9F function to get the empirical influence values. Obviously, stuff that's from part B should match up with what's in part A. Now, based upon what we just talked about in class here today, now you know how to use the Jackknife and regression-based estimates. Make sure you put them in a nice little data frame to make side by side, so for every observation I can see easily what the different estimates are. Part C, something we haven't talked about. Examine how well the linear approximation for variance of t works. Now, for the first three methods listed here today at the beginning of class, those all rely on a linear approximation to the statistic. And so the book discusses, and I'm not going to discuss it in class because I want you to make sure that I want to make sure you're reading the book and that you can actually take what you learned in class to and figure out how to use a particular new function, which we haven't talked about. But the book has a nice little interesting way that the Bootstrap can be used to evaluate, does this linear approximation actually work? Obviously, if it doesn't, what do you think your variance estimate is going to be? Is it going to be good or bad? Well, bad. So we have a nice little way using the Bootstrap to figure out if a linear approximation actually is reasonable. And so that's the purpose of part C, for you to use the linear.approx function to figure that out. Note that I do tell you what to use for R in terms of number of resamples and also the C number. Something I didn't realize until I was reviewing my notes for class is that I forgot to mention to use the exact same ones for the regression-based systems. And these resamples and the C number are exactly the same for project control. So part D then says, well, just kind of summarize everything that you've done. And note that the last two basically come from project number 1. And let's just compare. Part E. Now this gets into what I was just saying about a minute ago. And that is, why are we looking at these variance ways to estimate the variances? And one of the reasons is because we need to get this Z star value. And so why don't you find the 95% studentized interval for theta? And it just so happens, as you will find out, is that this interval will be exactly the same as what you got from project number 1 because of the variance estimate ends up being used for the non-parametric delta method. And but you're going to, if you remember from project number 1, the interval was quite wide. And so now I want you to, examine these Z star values. Tell me why you think this is happening. And then you'll get at a root problem, you could say, of using the studentized interval. You know it's one of the best Bootstrap confidence intervals out there. This one and another one called the BCA interval that you learned about in Chapter 5 are the two best. The interval can be quite wide. And finally, part F. Examine what happens to all 5 methods of estimating the variance as the sample sizes increase. While these are non-parametric methods, still you would hope that all of them are going to get to eventually the same spot in terms of the same estimate as n increases. Otherwise, you might be worried if maybe they're not consistent estimators. Well, let's actually do very little simulation. Simulate one sample from a normal distribution there. It uses the observed mean and observed. I don't remember. See what is this?
That's what they told us.
That in Excel work. Okay. So where we have these particular values of n, and set a C number just so that everyone gets the same answer, and see what you get for your variances. What happens? Are these variances becoming about the same? Guess what they are. And just show me that that is actually true, and also comment what happens to the linear approximation as well. Does it get better? Does it get worse? Hopefully, it gets better. You got to remember the form of a linear approximation. Typically, you have your statistic of interest is approximately equal to something that you calculate plus some other stuff. Let's see. That's usually that remainder term that we talked about in the past. It's called R sub n. And hopefully that remainder term disappears once n gets big, meaning the linear approximation will get better and better and better. Show me if that actually does happen.
We use the same 7818 before running boot.
Yes, please. And use the same C number before every sample. That's not something we typically do in research, but it's just easier for me to give you one C number versus 5 different C numbers for 5 different samples.
So that seed for generating our samples out of the normal, and then the 7818 for doing boot when we need to boot for the regression.
Yep. Okay, so that's project number 2, yes.
I just want to clarify, you said for part 1A and BI that they should match.
Yeah.
Not necessarily exactly correct, but very, very close.
Very, very close, yes, because you're taking numerical derivatives, and there should be probably a small...
Okay.
Any other questions? Okay?
What's the 1E reference in question F?
Do you mean 1D maybe?
Yeah, 1D.
Okay.
Thank you. Okay. So let's move on. Let's talk about the double bootstrap. I briefly mentioned it before. And all it is you're basically taking a resample from your resample. In fact, you could have a triple bootstrap, a quadruple bootstrap if you really wanted to, but it gets to a point where it's just going to take a lot of time to do. So, usually you just see up to a double bootstrap. Okay. So we were again talking about, we have this, studentized statistic here. And I purposely wrote it this way so you can see this as a function. So V is an estimator of the variance of T given F. How can we estimate V? Well, we've talked about this. I'm going to make a slight notation change here. It's very minor, but it might help out a little bit later. How can we estimate this V? Well, let's call this estimate in this particular section to kind of duplicate what that book is doing. Let's call it V boot. Help differentiate from all these other variances that we're calculating. And you go take our resamples and calculate the usual, do the usual calculation. Now note though that with this we are not making any we're not making any kind of assumptions about a particular functional form to V. With the other three methods that we talked about here, you have a specific functional form that you can write out. And it's based upon this linear approximation. VBoot does not rely on any kind of linear approximation. So what happens if we want to calculate now Z star? As we were discussing, well, change the F's to F hats, change the F hats to F stars, and get this quantity here so that T star has to be calculated for every single resample, V star has to be calculated for every single resample. Calculating like a V star like quantity is easy to do, like with, for example, the nonparametric delta method, because you have the actual formula, and everywhere you see a Y, put a Y star instead. But now, what happens if you were really wanting to use the bootstrap instead for this V star quantity? Well, then this means that you're going to do you could say, a second layer of resampling. So, make sure I'm... So let's say for R equal to, little r equal 1 to capital R, you're going to calculate this studentized quantity. Note that I put a V star boot there. That was better notation. And this V star boot comes from the second layer of resampling. And this is what it looks like. Let me explain the notation here. I'm going to take M resamples from the first, let's say, resample, and that's going to give me V star 1. V star 2 results from taking M resamples from the second original resample. Is everyone clear on that? So let's say I have this as my data set, Y1, Y2, Y3. My first resample then would be, let's say, Y11 star, Y12 star, Y13 star. then if I were to take a resample from this resample itself, so let's say m equal 1, I get y1. Let's see how I want to do this. Let's do it like that. Yeah, this notation is not going to be the best, but I think you get the idea. So if I take my resample from this original sample, then I'm going to get y11 star star, y12 star star, y13 star star. Maybe actual numerical values might help too. Let's say I have 1, 2, and 3 as my original data, so the y's. Then let's say y stars could be maybe 1, 2, and 2. Then y star star could be 1, 1, 1. Notice you can't have a 3 here. So 3's can't occur. Okay, is that clear on the notation now? So my variance then, for taking m resamples, is 1 over m minus 1 times the sum little m equal 1 to capital M. And this T star star with subscript RM means it's from the R3 sample, the mth, you could say resample. Okay? Minus T star star bar sub R. So for the R3 sample of the M resamples that M resamples you've taken, you find the mean of them. So again, what this is going to mean is if I have, let's say, 1,000 original resamples, I'm going to have 1,000 V stars. And perhaps capital M is maybe, let's say, 500. So that means I'm taking 500 resamples for every single original resample. And you can see there's a lot of resamples. In fact, you have your original R resamples, and then for every single resample, you're taking M resamples. So you're going to have R times M plus R total overall resamples. That's a lot. Authors of our book caution about the time needed to implement double bootstrap here, but that was a long time ago. You know, people are usually hesitant about actually using the double bootstrap, I think, because you don't want to have to take a resample. But I don't think it's that big of a deal. In fact, when I was at the joint statistical meetings in August, I went to talk from F1, and he was mentioning the double bootstrap. That would be another way to approach the problem that he's talking about. So, anyway, so let's take a look at an example. Now, coding this into R is not necessarily, it's not that bad, but you just got to be careful what you're doing. So this is with the AC data again. I have a program called double_boot. First thing I'm going to do is I'm going to calculate my statistic using my usual calc.t function. Let me actually show you in Word. So here's my usual calc.t function. Now, like I normally do, I get my data, my resample, using the corresponding indices that are passed into calc.t, and then I implement the boot function. So, what's my data? Well, it's my resample. The statistic I'm going to calculate for every resample is calc.t2, which is basically kind of the usual kind of function that we see, but now, we'll just calculate the mean there. My number of resamples that I'm going to take is m, and semi-coordinate. Then, v.boot, when this is actually run down here with the boot function, this is going to give me v star boot r. When it, make sure this is clear, when run with, and then what I'm going to pass back at the end, the mean of D and V boot. So the first time I run it, here's T. This, again, I'm just testing it out. And this is just V boot, because it's just with the original data. Is that clear? And then, when I actually then run this calc.t function with the boot function itself, I run it like I would normally. So here's my calc.t. And so, let me actually do this now. So this is where I ran it with the original data. And if I look at the head of boot.res, $T, here is T star 1. This is V star 1. Okay.
Why, so originally when you showed the 108 and the 1440 based on the original data, why don't we say like V hat? Because I mean, it's based on the same.
Well, yeah, it's just a problem with notation that I think our book has. That's all. Yes, this is the variance hat of T. The problem is that notation doesn't say what kind of estimated variance is it. Is it based on Bootstrap? Is it based on Jackknife? Is it based on what? And so now that we have these 4 different estimates of the variance, now our authors say, okay, let's focus on using notation like this. Are there other questions? Okay. Let me show you a few other aspects of this code. The first one up here deals with checking how long a function takes to run. This is useful for some stuff that we're doing because we're using simulation to do our calculations. And depending upon the statistic and how many resamples that we're going to use, sometimes it's good to have a general idea of how long something's going to run. And so you might, let's say, test the code with maybe a small number of resamples and then project up to the larger number of resamples that you want to use eventually, so that you know that there's not a problem with your computer that's causing it to run so long. It's just that the calculation's taken a long time and you have already estimated how long it would take. So one way in R then to figure out how long some code takes to run is as follows. At the top of your code that you're interested in, run the function proc.time, which finds the current time. And I usually put in an object called like start.time. And then at the very end, once you get done running all your code, run proc.time again and put it into an object called end.time. Simply subtract the 2 times, and you can look at the contents of the result called save.time if you want to. But the main thing is that the third element gives you the number of seconds. And if I divide by that by 60, that will give me the number of minutes it's going to take to run. So in this case, it took me 0.12 minutes. This is a very useful set of code to keep track of time. You know, even outside this class, I would expect all of you will have some experience where you're going to need to do some Monte Carlo simulations to examine your research. Well, you know, you run your simulation first for all the simulated data sets that you want to run. Instead, try for, let's say, 10 simulated data sets, see how long it's going to take, and then if in the end you want to, let's say, run for 1,000 data sets, well, take the time that you get for those 10 data sets, multiply it by 100, and there you go. Now you know how long it's going to take. A simple tool. There are other functions that are now available in R to allow you to check time, but I think this just works fine. So that's why I still use it. Another little thing that I want to mention. Notice what I chose for M. You know, I'm trying to duplicate an example, so that's why I use 100 here. Our authors recommend 50 to 200 for M. Originally with Bootstrap research in the 80s and most of the 90s, in the 1980s and 1990s, people thought that you could get away with a relatively small number of resamples in comparison to like confidence intervals to get a good estimate of the variance. But a paper that appeared in American Statistician in 1998 kind of said, okay, that's our original line of thinking might not be good. And they recommend just in general, whenever you're calculating a variance with Bootstrap, not necessarily with the double Bootstrap, in general, use at least 800 resamples. So, you know, if I were to put this into practice, I would not use 100 resamples here. I would actually use a larger number at the second level. Of course, though, remember what that's going to mean, though. It's going to take a lot longer, too. But, you know, relatively speaking, it's not going to take that long a period of time. I think I actually ran it with 800 and on page 55. You see it took me, you know, a little bit less than a minute. Of course, if you're actually doing a simulation study where you needed to use the double Bootstrap, you know, then you start thinking about, okay, now it takes me a minute to calculate variance, and I have to do this for now 1,000 data sets, let's say. Well, then you start thinking, maybe I need to do something else. Anyway. Okay, so on page, so also what I do here, I calculate Z star just so that we can take a look at the distribution itself. I just kind of summarize it a little bit. Let's actually take a look at it here. There you go. And this is what we get for Z star. So notice it's kind of distorted a little bit. Any thoughts why? It's just distorted. It's very. There's some very, very few things way out there. Yeah, maybe we have some very small variances in the denominator, and look what's going to happen then to Z star if you have a small variance. It's going to really jack it up. that note, what I just said might help you on a particular part of the project. Well, how about we take a look at a histogram of these variances, where I actually did standard deviations that we get. So here's a histogram. You can see it's quite bimodal. It's just quite bimodal. It is bimodal. I don't want to be sure. It is bimodal. Why do you think that occurs? This corresponds to a discussion we had maybe last week, or maybe the week before, regarding this data set.
That largest observation.
Yeah, that largest observation. When that largest observation is in there, generally speaking, you're going to get stuff over there. When it's not in there, you're going to get that. So that's why that happens. Yep. Okay, so then that concludes Chapter 2. I will tell you that, I forgot to mention this, that the double bootstrap stuff is not on test number 1. It could be on test number 2. In fact, we will come back to the double bootstrap in Chapter 3. So test number 1 material stops on page 250. Okay, finally, Chapter 2 is done. Any questions? Okay, so let's start Chapter 3 then. So Chapter 3 has a number of topics that are kind of, somewhat disjoint. They don't, in Chapter 2, the topics, to some respect, kind of built upon each other. To some respect. Not totally, but kind of. Chapter 3 more has disjoint topics. And that's why it's called Further Ideas. And the first thing that we're going to talk about in Section 3.2 is, well, what happens if you have samples from several populations? So let's say population 1, population 2, up to population K. How does the stuff that we've been doing change? Let's talk about that. It's really not too bad. So let's say I have K different populations, and I have distributions F1 through Fk representing those corresponding K populations and the corresponding estimates F hat 1 through F hat K. I have a sample from population I. Notice that I put in the first subscript the sample number, or population number, and the sample size from population I is n sub I. I can take my resamples as you would expect, but note what's in capital letters there. The resampling is done within a particular sample. So if I have a sample from population 1, when I take my resample, I just focus on that particular population number 1 sample. When I do resampling with respect to population 2, I just focus on the sample from population number 2. Forgot to mention this before. I have independent random samples from the different populations. Okay? That's why I take these samples that way, or resamples that way. So to some respect, you can kind of think of what we're doing here as basically a stratified resample. You've probably heard of stratified sampling in another class before. We essentially have stratified resampling here. We can represent our parameter of interest now in terms of statistical functionals, where now I have the K different Fs, and also our statistic is represented in a very similar manner. Now, yesterday when I was taking a look at my notes, I thought that maybe how to find influence functions was not as clear as I would have liked, so I ended up this morning actually uploading a slightly modified version of my lecture notes, which is basically here down to here is new. If you want to, you can copy this, or you can just wait until after class and just download that part of the file. It's up to you. So, just like in section 2.7, we want to find out influence functions. And to make things easy, let's suppose that we have just simply two populations. And also to make things easy, suppose we have a statistical function that represents just stuff from population 1, and we also have a statistical function that represents stuff just from population number 2. So let's call this whole thing together using kind of notation that we did in section 2.7, A of T1F1 and T2F2. So perhaps, and this is going to correspond to an example coming up, perhaps this T1F1 is, let's say, population mean for population 1, and T of F2 may be the population mean for population number 2, for example. Then the influence function then for T1F1 is basically kind of what you would expect, but we just need to be a little careful here. So when I take the derivative with respect to epsilon, notice only the T1 stuff has this mixture distribution in it. Only the T1 part has the mixture distribution in it. Find the derivative, set the derivative equal to 0. I'm sorry. Well, we set derivatives equal to 0, that's why I wanted to say that. Plug in epsilon equal to 0 there. And then the influence function for the second statistical function is basically the same idea where we only use that mixture distribution inside this second part there. If you have m different, let's say, statistical functions, then you just proceed in the same kind of manner. And that gives you the empirical, gives you the influence function. Well, how do we use this? And now this should correspond to what was already in the notes. Well, we can use this information to get variances. So the nonparametric delta method, the extension that you would basically expect. Before we had, 1 over n squared times the sum of the LJ squared. Now, since we have, let's say, k different populations to worry about, we need a little subscript on the L to represent the particular population. And we still take the sum of the L's, square them, and now we take the sum over the k different populations. And notice we have the 1 over n squared still corresponding to what sample. So L sub ij is the empirical influence values for the jth observed value in the ith population. How do you find the empirical influence values? Just like what we've done before. We can also have VJack, VReg as well. When you calculate these in R, you've got to be careful. You can use the EMP-INF function for all of these, but you need to make sure that you use the strata option. And you'll see an example coming up, which is option strata argument. That's in the EMP-INF function. That helps R to know with the original data, did it come from population 1, did it come from population 2, did it come from population 3, and so on. Also, in the var.linear function, there's a strata argument as well. And as you will see too, with the boot function, there's also strata arguments. Okay, so let's take a look at an example. This corresponds to example 3.1 and 3.3 in the book. Let's say that our parameter of interest is simply the difference of two population means, mu1 minus mu2. So we could actually represent this in terms of a statistical function. The corresponding plug-in estimator replaces the f's with f hats. We get y bar 1 minus y bar 2. Now, before taking this class, what you would use to estimate the variance, how about we just call it V, would be the usual unbiased estimate of the variance for T. Nothing surprising there. then how would you actually then calculate them in terms of resamples? Well, again, resample within a particular, let's say, population. You get T star, you get Y bar 1 star minus Y bar 2 star is what you would expect for what the sample means would be. And if one wanted to, one could calculate then V star, let's say, as this here. Well, what about now the nonparametric delta method? Let's make a note to myself. Well, the empirical influence values. Well, I'm sorry. Well, let's actually talk about. Let's go back to this journal. Let's first talk about what the influence functions are. So LT1 then would be equal to the derivative with respect to epsilon of, let's see how I'm going to write this. One minus epsilon integral y df1. Let's also put a subscript 1 on y as well. Plus epsilon integral of y1 dh y1 plus mu2. I'm sorry, minus mu2. Evaluate this at epsilon equals 0. Is everyone clear on that? So when you take the derivative, look what happens. First of all, that mu2 disappears. So there's no epsilon there. And you're left with what we've basically had before. Let's see now. y1 minus mu1. Evaluated at epsilon equals 0, which of course is 1 minus 1. Let's talk about LT2. So the partial with respect to epsilon of mu1 minus 1 minus epsilon integral y2 df2 plus epsilon integral y2 dh2 hy2. And all of this is evaluated at epsilon equals 0. So the mu1 part disappears, and what you're left with is this, minus y2 minus mu2. So notice how that minus now is in there. So the empirical influence values then, well, just plug in corresponding estimates. Put a subscript j on the y's. And then the nonparametric delta method estimate of the variance comes about really simply. And it's what you can say would be the usual bias estimate of the variance. Because we're dividing by n sub I versus n sub I minus 1. For these L's, I could use Jackknife or regression estimates too. Okay. Let's take a look at an example. So I call this example 2 means. There was no actual, well, they have a different data example in the book, and I believe that's actually a homework problem, where I basically did most of the work for you. And so I just have a different example here that corresponds to the non-data example that they presented in the book. How about we just simply simulate some data and look what happens. So what I'm going to do is set a seed. I'm going to have two sample sizes, so N1 is going to be 20, and 2 is going to be 15. I'm going to have two means. Mu1 is 14, Mu2 is 10. I decided just to use simple exponential distribution, just so it wasn't just necessarily normal, and also we get some skewness involved to see what would happen. So I simulate some data from random exponentials. I put them in y1 and y2, and this part's really key next. In order to get the boot function stuff that we're going to do to work, the most convenient way to structure your data comes from multiple populations is to construct a data frame, where this data frame has your data in one column, and then let's say your sample or your population number in the second column. That's the most convenient way to work with this form of data. So what I did here was I used the data.frame, and I created a variable called y. I put all of y1 sample values in it. I create another variable called pop for population, and I give it a value of 1. Now note that y1 actually has 20 different values in it. Pop obviously has one value. What happens? The 1 gets repeated 20 times. That's what's called recycling in R's terminology. Then I also create another data frame, and notice I use exactly the same variable names. Y is equal to now the stuff that's in y2, pop equals 2. And so I have one data frame here. I basically want to put another data frame right below it, so I use the rbind function, row bind. And this is what it looks like if I use the head and the tail function with it. So to do the bootstrap, we use the boot function. So I'm actually looking at, sorry, I know there's a lot of code here. Unfortunately, we're not going to be able to get through all, I don't think. Page 3.7 at the top, where you say bootstrap it, or what?
We were looking at your head and your tail of your data.
Yeah.
And since N1 was 20 and N2 was 15, shouldn't we just have 35?
Thank you for bringing it up. That is correct. This is what happens. So let me actually run this code. It's kind of an annoying thing that happens. Well, that's interesting. It didn't occur there. Perhaps they have fixed the annoying aspect of R since I have last run this. But what would happen is that with this data frame, you will have automatically, these row numbers put there. And then with this data frame, you will have those row numbers put there. And so when you take one data frame and put it right below the other, well, what does R do with those row numbers? And what happens here is it basically put a 1 in front. I think. Well, basically what it did was it
Put a 1 at the end.
put a 1 at the end.
Okay.
Put a 1 at the end. So, where we see 15 here, that's why you see 151 on page 3.5. But it looks like now that doesn't happen, since I originally had created these notes. If you ever wanted to get rid of those numbers, there's a row.names argument that you can also put in there. And I think it's row.names null. Null? Let me take a look at this. Row.names. Is that what I did?
That's the default, so that's what gives you the numbers. I think if you give it a list of the names, you can put actual names.
Yeah, but I didn't want any names at all. And I thought that would... I thought there was a way that you could get rid of those names from printing altogether. And for some reason, I don't remember exactly what it was, because obviously I didn't get it right. Anyway, it's not a big deal. It's just kind of an annoyance. And with that, we only have about 3 minutes left, and I know for sure we're not going to be able to get through all of this. Are there any questions? Okay, that's it for today.